I shall show you some figures, and you can see these figures. You can see that here we have 3 types of figures. Okay, one is having local minima. Okay, another is having local maxima, and another is having neither maxima nor minima. But at the same time, the derivative will be 0. Okay, so this is an example, and again you can see that this is a point in which it is not maximum, or also it is not minimum. Okay, so in this case also you can see, you can see that this point is neither maximum nor minimum. Okay, neither maximum nor minimum. Here also you can see some figures. This is the example for saddle point, neither maximum nor minimum. Okay. Yeah, here this is local unity case, this is local minimum, this is local maximum, this is local maximum, and this is in this point the derivative is 0. At the same rate is neither maximum nor minimum. Okay, we are discussing the multivariate case, so you can see this type of figures. I think you got the idea of maximum minimum. This is some another figures that you can see. This is an example of saddle point. It is neither maximum nor minimum. Okay. In this case we have minimum, minimum not maximum, and this we have already seen. So this type of points are called saddle points. So 3 points, we are discussing about 3 points, how to mathematically verify a point is maximum, a point is point of minimum, or a point is saddle point. So there should be some criteria. So we are discussing that criteria for identifying a point as maximum or minimum or saddle point. So that can be discussed as a theorem. Okay. So this is the brief description of the discussion now we have done. So the criteria is nothing but that is given in this theorem, theorem 7.7.1. F from D to R, where D is subset of R is n. Suppose that F has a continuous second order partial derivatives in D, and if x0 is a point of F, then at x0 F has the following. There are 3 possibilities. Okay, the minimum requirement is F has continuous second order partial derivatives. Okay, F has continuous second order partial derivatives. That is the minimum requirement. And the x naught is a stationary point, that is either maximum or minimum or saddle point. It's a stationary point of f. Then x has the following. S has to be x naught satisfy the following conditions. Okay. The point x naught is a local minimum if h prime del square f of x naught is greater than 0, like as we seen in this figure. Okay, this is a del is a h prime del square f of x naught is greater than 0. In the univariate case, we know that f double dash. In the multivariate case, we can represent like this: h prime del square f of x naught greater than 0 for all h equal to h1, h2, hn prime in a neighborhood of 0, where the elements of h are not all equal to 0. Okay. Second condition is a local maximum if h prime del square f of x naught is less than 0. Okay. As we see in this figure, this is a point of maximum, local maximum. So in that case, we can say that x naught is a point of local maximum if h prime del square f of x naught less than 0, where h is same as in case 1. A saddle point if h prime del square f of x naught changes sign for the values of h in the neighborhood of 0. Okay, that's the condition for the saddle point. You have seen the saddle point or the type of saddle points. The mathematical expression is, or verification can be done through this third condition. So let us start the proof of these 3 points. We know the Taylor's theorem. We have already discussed that Taylor's theorem. F of x naught plus h equal to f of x naught plus h prime del f of x naught plus 1 by 2 factorial into h prime del square f of z naught, where z naught is a point in between x naught and x naught plus x. Since in this theorem we have assumed only second derivative, so we can take only two terms. Okay, so we consider only 2 derivatives for the in the Taylor's theorem. Okay, so this is the form of the function using Taylor's theorem. Since x naught is a stationary point, then what is the speciality of stationary point? The derivative, first derivative will be 0. Okay, first derivative will be 0. That means it should be a smooth edge point. Okay, it should be either maximum or minimum or saddle point. So let us rearrange this theorem statement. We can see that f of x naught plus h minus f of x naught equal to half into, what is that, 1 by 2 factor, because the second time becomes 0, because we are considering only saddle points. So this time will become 0. So just the remaining time only, that is 1 by 2 factor into h prime del square f of z naught. Okay. Moreover, we know that we have assumed that the second order partial derivatives are continuous. Okay, so the right hand side is continuous. This right hand side is continuous. What is the speciality of continuity? Yeah, you can see that it is continuous at x naught. So, for example, what is the definition of continuity given epsilon greater than 0? There exists a delta greater than 0 such that mod f of x minus f of, so in this case, mod f of x naught minus mod f of x, z naught minus mod f of x naught less than epsilon. That means the distance between f of x naught and f of z naught is negligible. So f of z naught will be equal to some f of x naught plus s smaller quantity. So similarly, we can apply same argument here. So this will be, this right hand side will be 1 by 2 5 into h prime del square f of x naught plus a small argument. That is order of knowledge. Okay, so by applying the continuity argument, we can write like this. Okay, where h equal to h prime h raised to 1 by 2, and order of h is a number. It's a small increment, is a small positive quantity going to 0 as h tends to 0. Okay. We note that for small values of knowledge, the sign depends on the value of, okay, because we are considering arbitrarily small, order of which is going to 0. So if the first term in the right side is positive, the left side will be positive. In if the first term in the right side is negative, then the left side will be negative. We cannot we can neglect the order of knowledge term, because that is a very small quantity. Moreover, it is going to 0 as h going to 0. So the sign of f of x naught minus f of x naught plus h minus f of x naught depends on the value of first part in the right hand side. Okay, value of h prime del square into, h prime del square f of x naught. So the sign of left side depends on sign of first term in the right side. Okay. So what happens? So that if the right hand side, first term right hand side is positive, then f of x naught minus f of x naught plus h minus f of x naught is greater than 0, or in other words, f of x naught plus h greater than f of x naught for all non-zero values in h in the neighborhood of 0. Thus, x naught is a point of local minimum, because for all nearby points, f is greater than f of x naught. Okay, the minimum value is attained at x naught, that is f of x naught plus h is greater than f of x naught. So the minimum value is f of x naught. Okay, so that is a point of, so x naught is a point of local minimum. Similarly, we can say that if the right hand side, first term the right hand is less than 0, then f of x naught plus h minus f of x naught less than 0, or in other words, f of x naught plus h less than f of x naught for all non-zero values of h in some neighborhood of x0. In this case, x naught is a point of local maximum, because for all nearby points of x naught, f of x naught plus h is less than f of x naught. Okay, like as we seen in this figure. So consider for this point, here it is f of x naught plus h. Suppose this is the point function value for the point x naught plus h. So in this case, f of x naught plus h will be greater than f of x naught. If f of x naught plus h appears here, you can see that it is make it x. Okay, let us, I shall draw it. Suppose this is the what is this? This one is what is this? Can you say f of x naught plus h? Okay. What is this? This is the point of x naught. Wait. Point f of x naught. Okay. So in that case, if we consider another point here, you can see this is also greater than f of x naught. Greater in the sense of multivariate setup. Okay. Similarly, in this case, you can see that this is, suppose this is the point f of x naught. So and suppose we are considering another point sum of x naught plus h, and suppose this is the location of f of x naught plus h. What happens? Yeah, this is f of x naught. So all the f of x naught plus h will be less than f of x naught in the multivariate setup, in the multivariate sense. Okay, that is explained here. F of x naught plus h is greater than f of x naught, and f of x naught plus h less than f of x naught for all non-zero values in h in some neighborhood of x naught 0. In this case, x naught is a point of local maximum of f. And what happens in the case of saddle point? H prime del square f of x naught changes sign inside the neighborhood of 0. Then x naught is neither a point of local maximum nor a point of local minimum. Therefore, x naught must be a saddle point. So you can see that figure, the third figure. Yeah, when we look at this figure, what happens? Suppose we are referring this point. This point. Suppose we are referring okay. Suppose x naught plus h is here. It is below. Suppose x naught plus h is here. It is above. So we cannot say always. Okay. Here always f of x naught plus h is below. Here also always f of x naught plus h is above. Here that's not happens. Sometimes it may be below, sometimes it may be above. Okay, so we cannot say this is a point of maximum or point of minimum. That is the idea. So that type of points are called saddle points, neither point of local maximum nor point of local minimum. Therefore, x naught must be a saddle point. Okay, so that this proves the theorem. So up to now we have discussed the maximum, the condition for verifying maximum or minimum or saddle points. So what are the conditions? Secondary positive, secondary negative, secondary equal to 0. Okay. So now we move to the some notations. So this is known as sign matrix. Okay, what is this? Yeah, f evaluated at x naught, that is f11. What is f11? Dou square f of x naught by dou x1 dou x1. Okay, what is f1? These all f values are f11, f5j values are secondary keys. Okay, so f12, what is f12? Dou square f of x1 by dou x1 dou x2 and so on. So you can substitute these values when you write in your notebook. Just write this one at first and then substitute this value for each position. Okay, so that is usually known as what is that? Assign matrix. Okay. Now what is h prime a h? This is usually known as quadratic form. Okay. You know what is quadratic form? What is quadratic form? For example, x square plus 2xy plus y square. That is an example of quadratic form. I shall show you. I think you study this in your matrix paper in the last module. Okay. You can see several quadratics. 2x square plus 10xy plus 2y square equal to 1. Okay, this can be represented as some matrix. A11, A12, A13, A12, A22, A23, A12, A3, A33 into column matrix. So this is a quadratic. This is some x prime A x. Okay. You can multiply y square plus 59 square plus 2xy plus 28 84y. That can be written like this. This is a quadratic form. Okay, this is quadratic form. Alternative expression of quadratic. X prime a x. So yeah, here we have used that type of notation. H prime a h. So what they say is this can be represented as a quadratic form. This x prime del square f of x1 using this Hessian matrix. Okay, A is the Hessian matrix. Now we can write alternatively. That means we have already proved this theorem. Okay, proved this theorem. At the same time, we have in matrix theory, we have what is that? Here, principal minor. Yeah, what is the principal minor? What is exactly principal minor? Yeah, this is the principal minor. Suppose we are considering a 3 by 3 matrix. Okay. We can take the first corner element A11. Take the determinant of A11. That is A11 itself. Now we consider the second row and second column and just take these 4 elements A11, A12, A21, A22. Take the determinant. Okay. And so on, continue in this fashion. So that are called principal binaries. Okay. Yeah, you can see example here. A11, A11, A12, A21, A22, A11, A12, A13, A21, A22, A23. So determinant of that are called first, second, and third order principal binaries. Okay. So that idea we are using here. Okay, for the proof. Let f be the same function as in the given theorem, and let A be the matrix given in the formula. That means is a sign matrix. And if x node is a stationary point of f, then at x node has the following. So we are rewriting the condition 1, 2, 3 like this type of principal minus. A local maximum if A is positive definite, that is the leading principal minors of A are positive. Okay, leading principal minors are positive. You know, you have to remember that this quadratic form is nothing but this one. Okay, so this one will be positive if and only if this one is positive. You also remember that this is positive only when this determinant of A is greater than 0 or principal minors of A are positive. You know, this is positive only when this is positive. This is positive only when all the principal minors of A are positive. So what happens? This is positive only when all the principal minors of A are positive. You got the idea? So this is the condition. The condition for local minima is this function is positive. That is we have already derived here. So from this principal minor concept, we can say that this is positive when principal minor of A are positive. So that is given as the corollary. Okay, a local minimum if A is positive definite. The definition is called positive definiteness. A is positive definite or if and only if all the principal minors are positive. So instead of principal minors are positive, the statement principal minors are positive, we can say that A is positive definite. Okay, so A is positive definite means the principal minors are positive. If the principal minors are positive, what happens? The principal minors are positive. This quadratic form is positive. If this quadratic form is positive, this one is positive. Okay, when this one is positive, we can say that x node is a point of local minimum. So that is stated here. A local minimum if A is positive, that is the leading principal minors of A are all positive. Yeah, from the first element to the total matrix. Here they have considered only 3 by 3 matrix. So just we will have only 3 principal minors. If there are 4 by, if it is 4 by 4 matrix, then we will have 4 principal minors. That is not given here. Yeah, this is the figure of representing the selection of principal minors A11, A12, A12, A21, A22, then 3 by 3, etc. Continuing this fashion, we get principal minors. Okay, and we have to continue up to the entire matrix. So that is the idea. So the next condition, similarly, we can say that for the second condition. Here we have to note that this is not all less than 0. When we say that it is negative definite, When we say that the matrix is negative definite, first element is negative, determinant of first element is negative, determinant of second principal minor is positive, and determinant of third principal minor will be negative, third principal minor is negative, fourth principal minor is positive, fifth principal minor is negative, etc. The leading principal minors of A have alternative sign as false. That is the condition for negative definition. Okay. When this condition satisfies, what happens? What happens? Yeah, we can say that this is negative. This is less than 0. When this is less than 0, actually this is less than 0. When h prime del square f of x is less than 0, we can say that what is that? X0 is a point of local maximum. So that is it. So from the principal minor of A, we can say that X0 is point of maximum or X0 is point of whether X0 is a point of maximum or X0 is a point of minimum. So a saddle point if either A is neither positive definite or negative definite. If we can say if we can ensure this pattern, we can say that A is positive definite. If we can ensure this pattern, we can say that A is negative definite. So if we cannot establish either of these conditions, we have to say that this is A is neither positive definite or negative definite. In that case, what is that? X1 will be a saddle point. Okay. So yeah, proof is given here. I have explained all these things. F is a local maximum. Yeah, F has a local minimum. It takes what if h prime del square f of that is exactly equal to h prime ah is positive for all s. That is A is positive definite. That is A is positive if and only if its leading principal minors are all positive. Okay. Similarly, in the second condition, h prime del square of x less than 0 if and only if A is negative definite. That is minus A is positive definite. Or we can say that leading principal minors of order m of minus A equal to minus 1 raised to m multiplied. Or we can say that it's alternatively negative and positive. Okay. So that is the condition for negative definiteness of principal minor. And in the third case, if A is neither positive definite nor negative definite, then h prime del square f of x1 must be changed in sign inside the neighborhood of x1. This makes x1 as a saddle point. Okay. So we have discussed theorem. You have to read this matrix theory from some other books. Okay. You can search for some matrix theory books, and in that matrix theory books, you can see some idea about matrix theory. Already പഠിക്കുന്ന ബുക്ക് എടുത്താലും മതി. Theory of matrices. Let us look at this. നിങ്ങളിപ്പോൾ പഠിക്കുന്ന ബുക്ക് ഏതാണ്? മാട്രിക്സ് തിയറി. Okay, anyway, so up to this corollary 2, you can write and submit. I think I will put the link there. No problem. You can read all these discussions. Okay, this is some special cases you can read and try to understand this concept. Okay, you can read up to this. Any one of you can take these examples as seminars. Okay, this is an example for what is that? Identification of stationary points. So one of you can study this example and these two example and discuss. അഖില വർഗീസ് സെമിനാർ എടുത്താണോ?
ഇല്ല.
അഖില വർഗീസ് ആണ് പ്രിപ്പയർ ചെയ്യട്ടോ. ആ ഒരു സ്പെഷ്യൽ കേസും അതുപോലെ തന്നെ 2 എക്സാമ്പിളും കേട്ടോ.
7.71 അല്ലേ?
നോക്കട്ടെ, ഇപ്പൊ കാണിച്ചത്. അതായത് 7.1 അതിന് മുമ്പ് ഒരു സ്പെഷ്യൽ കേസ് പറയുന്നുണ്ട്. ഇതിന്റെ ഒരു അതും കൂടി ഉൾപ്പെടെ കേട്ടോ കാണിക്കുന്നത്. ഞാൻ വേറെന്ത് പറയാനുണ്ട്? നമ്മുടെ ബുക്ക് നിങ്ങൾക്ക് ഗൂഗിളിൽ ഇഷ്ടംപോലെ കിട്ടും കേട്ടോ. നിങ്ങളത് വെറുതെ നമ്മുടെ ടെസ്റ്റ് മാത്രം അല്ലെങ്കിൽ നോട്ട് മാത്രം വെച്ചുകൊണ്ടിരിക്കില്ല. വൈഡായിട്ട് റീഡിംഗ് ഒക്കെ വേണം. ഇതൊക്കെ നിങ്ങൾക്ക് അറിയാവുന്ന വിചാരിച്ചിരിക്കും. പോളിനോമിയൽ എക്സെട്ര discuss the principal component, unitary matrix, quadratic form. This is quadratic form, general form. We have seen the example. This is general form. Example of quadratic form. You can see some examples of quadratic form here. Yeah, positive definiteness, positive semi-definite, negative definite, negative semi-definite, indefinite, etc. These are the condition. Positive and negative definiteness. This is the expression. Yeah, look at this conditions. This is some other theorems we will see later. Yeah, this is a principal minor. Okay. These are, they have given only definitions, formal definitions. Okay. This is example. Matrix theory ne പുസ്തകം ഉപയോഗിക്കുന്നത്. ഇവിടെ ബുക്ക് കാണുന്നില്ല. This is pure mathematical notes.